In this module, we are going to learn input-output matrices. One of the most important practical solutions in modern economics is the interdependence of the various industries of an economy. Suppose that each industry in the economy has two types of demand: internal demand, that is demand within the economy placed on one industry by another, and external demand or final demand, which is the demand from outside the system, say from the consumer market, exports, etc. It is important to analyze this inter-industry relationship of an economy so as to derive the conditions required to maintain equilibrium between supply and demand. Professor Wesley W. Leontief in 1951 invented a novel technique for this analysis called the input-output analysis. He developed an economic model of the United States economy by dividing it into 500 economic sectors. His work was first published in 1965 and he received a Nobel Prize in 1973 for his work. A review of his work was published in March 1995, Survey of Current Business. His work addresses to the question, what level of output should each of the industries of an economy produce in order that it will just be sufficient to satisfy the total demand for that product. Here it is obviously stated that an input is obtained and an output is produced. According to J.R. Hicks, an input is something which is brought for the enterprise, whereas an output is something which is sold by it. So an input represents the expenditure of the firm, and the sum of the values of the inputs gives the total cost which is borne by a firm, whereas the sum of the values of output represents the total revenue of the firm. The input-output model presents the interdependence and the interrelationship of the industries of an economy and within the economic system as a whole. After studying this module, you shall be able to get an idea of the input-output models which are of great practical importance in economics. Get an in-depth knowledge of static input-output model in its closed and open form. Formulate mathematically any inter-industrial dependence of an economy in terms of its output. Obtain the output levels for each industry of an economy to exactly meet the inter-industrial demands as well as the final demands. Let us commence this module with input-output model. Types and assumptions. The classical input-output models are of two types, static and dynamic. In this module, we will discuss the static input-output model. In static model, the output levels to be determined are seen in a particular period of time, say in a year. However, in a dynamic model, lags or rates of change over time of sectoral interdependence are considered. As a matter of fact, the dynamic version is an extension of the static model in consideration of intersectoral dependence involving rates of change of variables over time. The dynamic version would be discussed in detail in the next module. Broadly, the input-output model of an economy depends on two factors: the inter-industry requirements of the output produced by an industry. For example, if we consider coal and steel of industry of an economy, we know steel industry requires coal for its functional purposes, and coal industry also requires some of the output from steel industry for its requirement of equipment to be used for coal production. Final demand, which is the output needed to meet the external demands from the sectors outside the related industries of that economy. So the total output of any inter-industry sector can be used as input by other industries of that economy, by itself and by the sectors claiming final demand. Before formulating the input-output model for an economy, we will first state a set of assumptions. First, each industry produces only one product, and if more than one goods are produced by an industry, then they are produced in a fixed proportion to one another. To produce its goods, each industry must use goods produced by some other industries of the economy, thereby forming interdependence amongst the industries. The output of each industry are completely consumed within the economy and meeting the final demand, if any, so no surplus output occurs. The input for an industry are in fixed proportion to the level of output. So k-fold change in every input will lead to an exactly k-fold change in output. Next, we will study some of the definitions. Input-output table. An input-output table presents the flow of goods and services between all the individual sectors of an economy over an added period of time, say a year. The time period can be taken as we are dealing with the case of static model. Input coefficient, the quantity of the output of sector I absorbed by the sector's J's total output is called the input coefficient of sector I into the sector J. It is usually denoted by Aij. Numerically, Aij is equal to Xij divided by Xj, where Xij is the output of sector I to sector J and Xj is the total output of sector J. Input output matrix, a complete set of input coefficients of all sectors of a given economy arranged in the form of a rectangular array, represents the input output matrix of the economy. In this matrix, each input coefficient Aij would be positioned in the ith row and the jth column. Production matrix. The matrix giving the amount of each commodity produced is called the production matrix. For an economy producing n commodities, production matrix is an n into 1 matrix denoted by x usually. Demand matrix. The matrix whose entries are the corresponding units of final demand from outside the economy form the demand matrix. It is an n into 1 matrix for an n commodity economy. Types of static input and output models. Open model, the input output model that allows for surplus from the production to meet the final demands from consumer, exports, etc., is an open model. Example 2 is the case of an open static input output model. Closed model is that the input output model for the economy in which all the production is consumed internally in the production process is called a closed model. Example 1 is the case of a closed static input output model. Now let us see some examples. Example 1. Consider an economy consisting of coal, electric and steel sectors. The output of each sector is distributed among the various sectors including the sector itself for its sum operation. Suppose that the total output is 100 units of the coal sector, 60 is purchased by the electric sector and 14 units by the steel sector. Of the total output of 100 units of the electric sector, 40 and 50 units are taken by coal and steel sectors respectively, and the rest of the 10 units are used by the sector on its own. Likewise, of the total output of 100 units of the steel sector, 60 and 20 are taken by the coal and electric sectors, and the remaining 20 the steel sector keeps to itself.
This information can be presented in the form of input-output table. Here units are taken in suitable multiples.
It should be noted that in this particular example, no final demand is considered for output, say the sectors. This would ultimately lead to a homogeneous system of linear equation which would be seen later. It should be noted here that the input-output table for the above example can be formed in terms of values as well. Knowing the price value per unit of output from each sector, it is more on the basis of priorities or interest of the decision maker as to what parameters are to be taken in any input-output table. Let subscript 1, 2 and 3 represent coal, electric and steel sector respectively. Then A12 represents the quantity of coal sector absorbed by the electric sector per unit of electric sector's total output, that is 100 unit, that is A12 is 0.60. Likewise, the other input coefficients can be determined.
For example 1, the said matrix is A, which is equal to 0, 0.60, 0.40, 0.40, 0.10, 0.50, 0.60, 0.20, 0.20.
Example 2. We consider another example that deals with the situation in an economy in a more realistic way. Consider a simple economy having just two basic products, rice and oil. To produce 1 unit of rice, 0.25 units of rice and 0.33 units of oil are required. And to produce 1 unit of oil, 0.08 units of rice and 0.11 units of oil are consumed. In addition to this, the two sectors of the economy have to meet an external final demand of 500 units of rice and 1000 units of oil.
Then the input-output table of an economy is given in the table form. Also, the input coefficients are A11 is equal to 0.25, A12 is equal to 0.08, A21 is equal to 0.11, and A22 is equal to 0.11, where subscripts 1 and 2 represent rice and oil respectively. So the input-output matrix is given by A is equal to 0.25, 0.08, 0.33, 0.11. Also, the demand matrix D is given by D is equal to 500,000. Moving on to formulations of models into a system of equations, first is closed input-output model. Consider an economy consisting of n independent industries, say S1, S2 to Sn. Let Aij represent the number of units produced by industry Si and absorbed by industry Sj to produce 1 unit for Sj. Then Xi is the production level of industry Si. So the total number of units produced by industry Si is given by A1i x1 plus AI2 x2 plus AIN xn. Since the economy is closed, the equilibrium condition is satisfied if the total production of industry Sj equals its total consumption, that is AI1 x1 plus AI2 x2 plus AIN xn is equal to xi for all I equal to 1, 2 right up till n. This results in the linear system A11 x1 plus A12 x2 plus right up to A1n xn equal to x1, a21 x1 plus a22 x2 up to a2n xn equal to x2, an1 x1 plus an2 x2 plus right up to ann xn equal to xn. Here the n into n matrix A is equal to A11, A12 right to A1n, A21, A22 right to A2n, then down to AN1, AN2 right to ANN is the input output matrix. And the n into 1 matrix X is equal to X1, X2 right up to Xn is called the production vector.
In general, the problem dealt for an economy is to find the production matrix X, which can be obtained by solving the above discussed system of equation for x1, x2 right up to xn. It can be done by implying some suitable techniques to solve the system of linear equation, as the system is of the form Ax is equal to x, that is 1 minus A x is equal to 0, where I is the n into n identity matrix and O is the n into 1 0 matrix. It is clear that the homogeneous system does not have a unique solution, which will otherwise be the case of trivial solution, giving production units of each industry as 0. So the system can be solved in terms of parameters using the Gauss-Jordan method or the echelon method.
Note, for a closed model, sigma j is equal to 1 to n, aij equal to 1 for all I equal to 1, 2 right up till n, as all production is consumed internally within the sectors of the economy, and so 0 is less than aij, which is less than 1 for all ij. Example 3. Consider a closed three-sector economy with the industries S1, S2 and S3 corresponding to agriculture, energy and manufacturing, where the input-output given table where the production units are suitably taken. Then the input-output matrix is A is equal to 0 0.2, 0 0.3, 0 0.2, 0 0.5, 0 0.2, 0 0.3, 0 0.3, 0 0.5, 0.5. Let x1, x2, x3 be the units of production required from the industries S1, S2 and S3 respectively to keep the economy in equilibrium. Then the production matrix is given by x is equal to x1, x2, x3. Now the system of linear equations in matrix form that represents the economy in equilibrium is given by Ax equal to x, that is 0 0.2, 0 0.3, 0 0.2, 0 0.5, 0 0.2, 0 0.3, 0 0.3, 0 0.5, 0 0.5 into x1, x2, x3 is equal to x1, x2, x3. Solving this system, we get the equations in the reduced form as x1 minus 25 by 49 x3 is equal to 0 and x2 minus 34 by 49 into x3 is equal to 0. Choose x3 as the free variable. We get x1 is equal to 25 by 49 into x3, x2 is equal to 34 by 49 into x3, x3 is free. Or choose x3 equal to 49r, which implies x1 is equal to 25r, x2 is equal to 34r and x3 is equal to 49r. Hence the production matrix is x is equal to 25r, 34r, 49r, where r is greater than 0. Next is open input output model. As discussed earlier, open input output model takes into consideration the demand DI from the ith industry placed by agencies outside the sector of the economy. So an additional factor of DI units needs to be taken into account apart from the constraints considered in the closed model. Using the same symbolic representations as done for closed model, we get the system of equations as a11x1 plus a12x2 right up to a1nxn plus d1 equal to x1, a21x1 plus a22x2 plus a2nxn plus d2 is equal to x2, then an1x1 plus an2x2 plus annxn plus dn is equal to xn. In addition to matrices A and X as considered earlier, we have the demand matrix D as well, given by D is equal to D1, D2 right up to Dn. So the system in the matrix form can be written as Ax plus D equal to X, or X minus Ax equal to D, or X into I minus A equal to D, or X is equal to I minus A raised to the power of minus 1 D. The matrix I minus A is called the Leontief matrix.
The previous system can now be solved using the available techniques. However, the solution to this exists as if I minus A is invertible and has non-negative entries. So, the components of X are non-negative. This would be an acceptable solution for this model. Example 4. Consider a closed three-sector economy with the industries S1, S2 and S3 corresponding to energy, manufacturing and labor respectively, where the input-output table is given.
Then the input-output matrix and the demand matrix for the economy is given by A is equal to 0.1, 0.1, 0.1, 0.4, 0.2, 0.2, 0.2, 0.3, 0.5. D is equal to 92, 69, 115 respectively. Problem can be represented in the matrix form as a system of linear equations is given by Ax plus D is equal to X, X is equal to I minus A raised to the power of minus 1 D. Here I minus A is equal to 0.9 minus 0.1 minus 0.1 minus 0.4, 0.8 minus 0.2 minus 0.2 minus 0.3, 0.5. By computation, it can be seen that I minus A raised to the power of minus 1 is equal to 1.47, 0.56, 0.521, 1.04, 1.86, 0.95, 1.21, 1.34, 2.78. And further, I minus A raised to the power of minus 1 D is equal to 235, 335 and 525. This implies 235 units from energy sector, 335 units from manufacturing sector, and 525 units from labor sector are required to fulfill on the whole the inter-industrial and final demand.
The type of solution to the open static input-output model as discussed requires the Leontief matrix I minus A to be non-singular, and in addition to all the output variables x, j need to be non-negative so as to make an economic sense. With reference to this remark stated above, in general, the Leontief matrix needs to possess certain properties called the Hawkins-Simon conditions, under which the determinant of Leontief matrix must be positive, that is I minus A is greater than 0. The diagonal elements of the Leontief matrix I minus A should be all positive, that is 1 minus A I j greater than 0, or equivalently A I j less than 1 for all I equal to 1, 2 right up till n. That is, the number of units of output of the ith industry required to produce 1 unit of itself should be less than 1. In case it is more than 1, then no net profit can be secured by that industry.
Now let us study economic interpretation of Hawkins-Simon condition. Consider a two-industry case in an economy. Let the input and output matrix be A is equal to A11, A12, A21, A22. The Leontief matrix is I minus A is equal to 1 minus A11 minus A12 minus A21, 1 minus A22. By first part of Hawkins-Simon condition, the diagonal entries are required to be strictly positive. That is, 1 minus A11 is greater than 0 and 1 minus A22 is greater than 0, or 1 is greater than A11 and 1 is greater than A22. That is, the amount of corresponding commodity used in production needs to be less than unity. Also, 1 minus A greater than 0 implies 1 minus A11 into 1 minus A22 minus A12 A21 is greater than 0, or A11 plus A12 A21 plus 1 minus A11 into A22 is less than 1. Since 1 minus A11 A22 is greater than 0, therefore A11 plus A12 A21 is less than 1. So the first commodity used as direct input for A11 and indirect input A12, A22, which gives the amount of first commodity needed in producing specific quantity of second commodity together must be less than unity. Consider an economy comprising of two sectors S1, S2 whose input-output table is given by. Now from the previous table we can form input-output matrix as A equal to 50 by 200, 75 by 200, 100 by 200, 50 by 200, which is equal to 0.25, 0.375, 0.5, 0.25. The demand matrix D is given by 0.75, 0.50. Let x be equal to x1, x2 be the output required to meet the entire demand. Consider the system ax plus d is equal to x, or x is equal to I minus a raised to the power of minus 1d. Here the Leontief matrix is I minus a is equal to 1, 0, 0, 1 minus 0 0.25, 0 0.375, 0 0.5, 0 0.25, which is equal to 0 0.75 minus 0 0.625 minus 0 0.5, 0 0.75. Now I minus a is equal to 0.5625 minus 0.3125, which is equal to 0.25, which is greater than 0. Also, all elements on the male diagonal of A are less than 1. Therefore, Hawkins-Simon conditions are satisfied. Hence, the system must have an acceptable solution as seen previously. X is equal to 1 minus a raised to the power of minus 1d, which is equal to 1 over 0.25 into 0.75, 0.625, 0.5, 0.75 into 75 by 50, which is equal to 3, 2.523 into 75, 50, which is equal to 350, 300. Hence, 350 units of output from S1 and 300 units of output from S2 would be able to suffice the entire demand inside and outside the economy.
Now let us summarize what we have learned. Input-output model was developed by Professor Vasily W. Leontief, for which he got the Nobel Prize in 1973. Input-output models are of two types, static and dynamic, each of which is of further two types, open and closed. In open model, the demand from outside the system of an economy are also catered to from production perspective, whereas a closed model is just sufficient to meet the requirement of inter-industrial sectors of an economy, representing the input matrix by A, production matrix by X and demand matrix by D. System of equation represents a closed static input output model is given by Ax equal to x, and for open model it is I minus a raised to the power of minus 1 d equal to x, where I is an n into n identity matrix for an n sector economy. To ensure the existence of an acceptable solution for the open model, Hawkins-Simon condition needs to be verified on the Leontief matrix I minus a.